materials, but and I work in the thing that's the domain. I've been developing this minimum intrusion grid. It's a middleware collaboration with some of my colleagues there. First of all, I want to say a bit about what I mean by the term grid. Grid was a big buzzword in the 90s, and as you probably know, much of that buzz have now moved on to the cloud. Yeah, sure. I think some of it is pretty much reinventing the wheel, but I'll cover that during the talk. So anyway, in the mid-90s, we had Ian Foster and Carl Kesselman presenting this whole idea of the grid. At that time, we had the internet where you could easily access all kind of information, but they wanted to take that idea and spread it out to all kinds of resources, that is accessing computing power, storage, even special devices like telescopes, accelerators, like the big accelerators that they have at CERN and so on. So they wanted this big unified access to all these resources, and they had a focus on including things like applications and also including people into the mix, focusing on sharing resources efficiently and enabling collaboration between users, especially using this term virtual organizations. I'll come back to that. So after a few years of development, we saw especially the Globus-based grid middlewares taking on, and they didn't really manage to capture the original vision, in my view. They worked quite well for the specialized people who were doing physics simulations and were able to send out the data to different machines and handle jobs like a big batch system. But the ease of use and the collaboration wasn't really part of the package. So we wanted to try to address that with this new grid middleware called Minimum Intrusion Grid, or MiG for short. And if I go back to the previous slide, the overall architecture in the Globus-based grids, the grids middleware that I call first generation, is this all-to-all communication. Users and resources communicate all-to-all. This gives some limitations to the whole idea. So we wanted to move on to an architecture where we had a centralized system of still distributed servers, but an actual system separating the users from the resources, where resources in this context could be clusters, supercomputers, and so on. We also wanted to move the actual grid middleware to these central servers so that we didn't have to force the users and resource owners to install a huge middleware and maintain that. So we moved all that to the central servers. Another part of the original vision was that the whole grid should appear like this huge virtual machine to the users, and by doing this completely different architecture, we could actually try to achieve that. From the resource perspective, grid should just be a set of users, or user accounts on the resource, so that would pretty much map to the existing system where they had local users already on the clusters. Back then, in the 90s, we saw a tendency for a lot of things that had previously taken place in labs in science, moving to simulations, and later on we saw business intelligence, data mining, also moving to computers instead of. So we suddenly had a large demand for computing power, and we needed to do it cheap. At the same time, we saw computing power being moved to data centers, where we had professional administrators taking care of all the maintenance. That would allow us to make it cheaper and more efficient, easier for the user, if, of course, we can provide some kind of interface for them that is familiar. So just to try to avoid the pitfalls that we saw from the first generation grids, we came up with these 4 rules that we try to follow very carefully. The first of them is the minimum intrusion. We don't want to force the users or resource owners to install anything on their computers. We try to keep everything on these MiG servers. The second one, which is probably a bit more important in in this context, is that we wanted to avoid the mess of tons of different implementation languages and simply stick with Python all the way through, unless, of course, there were some things that we could not work around. For example, when we work at kernel level for some advanced optional client features, then, of course, we had to go away from that one. But as long as we could, we stayed with Python. And, of course, we wanted to keep this transparency focus, to keep the ease of use and avoid users having to manually tamper with a lot of details that they don't really need to know about. Okay, so from the user side of things, we have users just have a browser, and they get a user certificate, which is a standard X509 certificate used in many grids, and they use that for their authentication and authorization to the grid. That's what they need for all the base use. If users want to do advanced stuff, for example, script a large number of tasks, then they can optionally download additional scripts for that, but it's not really required to use the grid. On the resource side, we try to limit it as much as we can. Again, we don't require any installation. Simply create a number of user accounts on the resource, that is on the cluster or supercomputer, and allow the MiG servers to access those accounts with an SSH inbound connection, and allows the accounts to connect to the MiG servers using HTTPS. Many of the other grids require special services and a lot of additional protocols that you need to open the firewall, and resource administrators typically just run away screaming when they hear those requirements. So we really try to limit it as much as we could here. Another point is that we just, the system administrators, that is the resource owners, are just ordinary users in the MiG context. So they'll have a user certificate, and they register the resource with MiG and use the web interface and the general interface to manage the resources in MiG. Later on, we introduced some kind of sandboxed resources as well that have even fewer requirements, but more on that later. So to keep with the idea of having a big virtual machine or big virtual computer for the users, we decided to stick with a model where we have a private user home for each user. So each user has his own user home on MiG, and when users want to use files, for example, when they use jobs, all file references are relative to the user home. So there's no need to specify my files are on this and this server, on this and this URL on the internet. You just reference them by the file path. And in practice, we've developed this web interface for file access. So it resembles any local file manager, so it should pretty much work like a big virtual copy of your local computer. You can, of course, edit files and manipulate them as you want to, and this is inline file editor, which is relatively simple, but it does your job for you. Okay, so generally, when you work with Grid, you have some tasks that you want done, and you split up the tasks into jobs. So you have some kind of batch commands that you want to run, and you need to specify how many resources those commands will use. For example, how long will it take to run them, and how much memory and stuff like that. And then, of course, if you have any input or output files from the job, then you want to specify that as well. So in MiG, there's an addition. Because we have this centralized MiG system of servers, you always just send your job to MiG and let MiG handle all the job control instead of having a local client keeping track of resources and jobs. So you send the job to MiG where the job is queued, and if you have multiple servers, then of course you can replicate the job to make sure that it isn't lost. And then when a resource is available, it will ask for a job, and MiG will schedule a suitable job for that job slot, send the job there, and make sure it gets executed. Of course, if something goes wrong and the job never returns, then MiG takes care of rescheduling it for another resource. So the user doesn't have to worry about this. If you want to cancel jobs or other way freeze jobs and stuff like that, you can of course do that, but otherwise you leave everything to the MiG servers. If you actually want to do grid-style applications, you again have some kind of interface, and then in the engine below, you split up the actual work and send it out as jobs. So that's a typical use. Again, to keep things simple, we made a web interface where you simply fill in the commands you want to run. In this case, it's the simplest job possible, hello grid. And if you scroll down, you can specify additional resource requirements. Then at the bottom of the page, there's a submit button. When you hit that, the job gets queued at the MiG servers, and you will see it in the jobs list as queued first, and then when it starts executing, you will actually see this top image where the job is executing, and then at some point when the resource finishes executing the job, it will automatically switch to finished. And then you can right-click on the job entry there and look at the results and output files and stuff like that. So in this case, I opened the status files that will automatically become available in your MiG user home, and you see they are quite cryptically named, but you have 4 files for each job: standard out, standard error, and 2 status files for exit codes. And in this particular case, I opened the standard out file, which just displays the hello grid. So pretty simple. As soon as you go beyond using just basic shell commands like the one I used here, you end up having to rely on the resources having some kind of software available for you. And we just reused the general idea of runtime environments that is pretty common for most bit middlewares. So users and resources can negotiate conditions for the job by setting up runtime environments and specifying which runtime environments you need in your job. So if you specify a particular runtime environment in your job, the job will only be sent to resources that actually advertise the corresponding runtime environment. So that's a one-to-one map there. For this particular case, I'll just show you a short example using a Python runtime environment. So we have a Python runtime environment that just indicates that any version 2.x of Python is available on the resource, and in the job we can use Python using the $Python environment variable. So in the actual web interface we have the list of runtime environments, and anyone can define new runtime environments, but it's left for the resource owners to actually specify that my resource implements this runtime. In the actual case of a Python job, I've taken a little sample here. It uses the Fibonacci number algorithm. So I have a Python application in my MiG home called fib.py, and I just opened it in the editor. It's very simple. It's just a naive implementation. It takes the 2 previous Fibonacci numbers and adds them up to the next number. So it recurses back that way. And then in the actual job, I'll take that from the bottom here, because first of all, I need the Python interpreter at the resource. So I specify I want a Python 2 runtime environment, and then I know from the Python environment that will enable the $Python environment in the job for me to use, so I don't have to worry about the actual location of the Python interpreter on the resource. and I specify my application and an input argument because in this case, I want the 26th Fibonacci number. In the list of executable files to my job, I specify fib.py because it's directly in the root of my MiG home directory, and then some additional specs because I know approximately how much I need to run this job. And then I get the job result back and have the 26th Fibonacci number. If there's time, I can show you afterwards actual small live demo, but I'll move on for now. So if we go back to the original vision for Grid, we had this important part about virtual organizations. So the point was that we want people from different organizations in the real world to be able to easily collaborate. For example, it could be people from different universities or different companies working together on a shared project. And we need some sort of means for actually enabling them to collaborate in an efficient way. So in MiG, we try to implement that in the form of what we call vGrids, which enables users to dynamically sign up for a collaboration and share files, share resources. They get access to private and public web pages that they can use for the project. They have wikis and version control systems for if they want to develop code. They might want to collaborate on keeping track of different versions. And then there's a small forum as well to ease communication internally. An important aspect here is that vGrids are completely user-managed. So all users in MiG can create their own vGrids and manage them. That is, sign up new users for them, decide who owns the vGrid and who can control the vGrid. They can even make nested vGrids to get some sort of hierarchy in the structure here. So I'm just going to show you examples of each of these features. So on the vGrids page, you can see at the bottom you create new vGrids, and that's for anyone to do. And then at the top there's the list of all the available vGrids. And these vGrids that you see here are the ones, some of the ones that I own, and that automatically results in full access for me to those vGrids. For members who are not owners of these vGrids, you will only have access to some of these features, the ones that aren't related to actual administration of the vGrid, but most of the features. So you can do all the collaboration, but if you're only a member of the vGrid, then you can't decide who else is member of the vGrid, for example. If you're an owner of a vGrid, you can go to the administration page and decide who's member and who's owner of the vGrid. You can decide which resources can participate in the vGrid, that is, which resources can take jobs from this particular vGrid and add storage to the vGrid. Just an example of a project using the web page for the vGrid, not very complex actually. And the same project has a wiki for internal documentation. There's a source code repository where the participants develop software for this particular project. And you can use the web interface for read-only access. This is a Mercurial repository, so this is also Python. And of course, you can use Mercurial clients from your local computer to have full read and write access to the repository. And in that case, you use your MiG certificate with Mercurial to get the same access control. And just a sample of the vGrid forum where you can communicate with other members of the vGrid. Finally, you see the resources that are actually participating in this vGrid, and you get all the stats and see how long time ago did they actually show up taking jobs. Okay, so that was a bit about the vGrids, the virtual organizations in MiG. So now I'll turn to resources in MiG. We have different resource models. First of all, we have a model which resembles the one used in many grid middlewares. That is just clusters and supercomputers signing up for jobs in a grid. In this case, we just try to make it a bit easier to sign up because you don't have to install anything. You just go to a web page and enter your specs for the resource, and then you can immediately use simple web buttons to start and stop resource in the MiG context. This also enables resources to deliver storage to particular vGrids in addition to just compute power. Later on, we developed another model to make it even simpler to contribute to grid, because we've seen a lot of these SETI and Folding at Home, Boink, all these public resource computing initiatives where people can contribute their spare compute cycles to compute-intensive projects. So we developed a simple screensaver application that simply launches a virtual machine that runs a MiG resource in it. So when the screensaver kicks in, it starts this virtual machine and then takes jobs. When the user comes back to use his computer, the virtual machine is killed, and any jobs running will be retried later automatically. So it gives an easy way to let people contribute. We made a live CD that allows us to put PlayStation 3s with powerful cell processors on the grid, and we did a proof of concept one-click resource model where you just use the Java virtual machine in a browser to open a single web page and start contributing to grid. When you have resources in MiG, they will appear under the Resources tab. If you own the resources again, you will have access to administrating them. Otherwise, you can just view the specs and see what resources are available. When you actually own a resource and go to the administration page, you have this. This is just a shortened form of the resource configuration, but there's also a full editing interface available where you have a form that is a bit more user-friendly to use when you want to specify the specs for the resource. Then at the bottom, you can see the actual controls for this resource in relation to MiG. You just hit the restart button here to start the resource on MiG, and it will start taking jobs. Okay, so as I started out mentioning, we've seen this bus going all the way to the clouds. First of all, we had the bus around grid, and after many years of grid middleware development, we kind of ended up with grid middlewares that were well suited for these very specific purposes of handling jobs in relation to, for example, high energy physics, where we had users that were quite knowledgeable about the underlying infrastructure and so on. So they could use it, and they still do that, but it was way too hard for ordinary users to just go on and use this for an easy way to use grid. So we saw this rise of cloud happening, and I'm not going too much into detail about this, but you probably know there are these three types of cloud definitions: software as a service, where you have web services; platform as a service, where you have some kind of software stack that you build your web service up on; and finally, the low-level infrastructure as a service, where you have some kind of virtualization, so you get what resembles a bare metal machine that you run your own entire operating system on. So how does that come into play in relation to grid? As we saw grid losing the hype because it's more and more turned into what I would call a job shop, where it didn't really deliver anything else but actual ways to interact with a lot of batch system around the world. It didn't really deliver on the collaboration, the ease of use in any way. So we saw users turn more and more to especially cloud computing in the form of infrastructure as a service, where people, instead of using a grid middleware, started deploying their own applications to cloud infrastructures instead. So you didn't have to worry about all these grid intrinsics. You could simply just build your own machine images and throw them onto the cloud and use that. And that works for people. So it's pretty pragmatic for people to choose that. I understand that, but of course we would want to try to see if we can do both and actually still get all the collaboration and ease of use while keeping, of course, the pros from both of these very hyped terms. So with this cloud computing, you may get some resource sharing because you may end up having virtual machines running on the same resources, but it's not really as a high level of sharing as you can get in the grid, where you don't have the overhead of virtual machines. And still, cloud is not that easy to use. You still need to have some knowledge about actually building your virtual machine images. So we'll try to revive the original vision of grid, and we already think that we can deliver the basic promises from the grid with our MiG middleware. We can share compute resources of all kinds, including these public resource computing resources. We have ease of use. Everything can be done with a web interface. You don't have to worry about actual file locations in your job. It's all transparent. And we do provide, especially important, these regrids that enables easy collaboration with workflows and communication that were part of the original vision. But still, we see the movement to cloud. So we thought, well, perhaps we can try to learn from some of the pros that we've seen in cloud and even integrate those ideas in MiG as well to make it even more complete. So first of all, why did people start to use cloud in such a big fashion? And one of the things that we saw was that it was simply too hard to get access to the software that you wanted to run on the grid. So people always ended up having to manually contact the system administrator on this resource and say, can you please install this software for me? And maybe it's 500 megabytes of software that the administrator doesn't have any clue about what it does. And that's always a no, I'll not do that. So we need some way of making that easier to work around that. Then we thought another one of the points of cloud is that you could actually have these web services and have the application platform. You make it easy for users to use an application through the web. Maybe we do something there as well. And finally, for the case where we still can't solve the problem of software deployment, then perhaps we could turn to virtual machines too and integrate that in the grid. So, first of all, on the better software sharing approach, we took a look at how things were, and we saw, well, we did have the runtime environments in place, but they were not always that easy to use because administrators still have to manually control applications on their resources. But perhaps we could make a system that would allow dynamic deployment of software to the resources. So we decided to go for a central software repository where we packaged some software and made it easy to deploy that software onto the resources. In this case, we found the brilliant Python-based zero install packaging system, which actually fits our purpose just perfectly, because it's a framework that allows anybody to package up software. You can do dynamic deployment because a software package is pretty much just an XML file pointing to an archive somewhere on the internet. And what zero install does internally is, instead of actually installing in the typical sense of installing system-wide, just pulls this archive down into the user account where it's cached and everything is run from this cache. So you don't have any super user privilege privileges involved at all. You can run anything from user space. You get automatic dependency handling and automatic updates. There's even support for isolating software internally in the account, and it uses cryptographic hashes to make sure that the software has not been tampered with. So this provides us with a way to actually let users package their own software, get it integrated in, for example, the software repository that we host, just put it somewhere on the internet, and then any resources that want to enable users to use these zero install packages just need to install a single zero install package, which is small and pretty well known, and that will allow jobs to use zero install packages on the resources. So that should make it easier for users to get the software they want on the resources. Then when we think about the other point I had from cloud was this application platform. And actually, when we think about it, we already have support for that because these private and public web pages that we provide with the regrids can be used for this particular purpose. Anybody in the regrid can actually build their own web application using these private public web pages. And then we provide a simple JavaScript library they can use to make it easier to actually split up the work into jobs and pull out the compute power into these web applications. Finally, we did some experiments with virtual machines, and we had a student too who integrated a virtual machine controller in MiG. This is still experimental, so it's not included in the production version yet, but we have it working in practice. So you simply use web interfaces to build your virtual machine image, and then you can use these buttons at the bottom here to actually fire out the virtual machines onto grid resources, and you can even get a VNC display running in the web browser, contacting the resource. So you can actually maintain this anonymity between resources and users because it all goes through the MiG servers. Okay, and another point to make it even easier and more transparent to users is that we provide SFTP access to the MiG user phones. And that also allows us, for example, if you have a Mac or a Linux machine, then you can simply use SSH FS to mount your MiG on locally, work on the files just as if they were available in the file system. And I do that every day in the projects I work with, which is quite well efficient. Okay, so I'm going back to a bit of the technical details in MiG here. As you've seen, a lot of it is web-based. So we have a web server, and we have different interfaces for that web server. We run WSGI, CGI, SMLRPC, so that users can decide which interface they want to use for this particular purpose. Then we have some daemons running in the background to actually handle the job. These daemons and the CGI all runs in Python. Well, CGI, SMLRPC use shared Python plugins. So I try to make an outline of how it all works. So of course we want to reuse as much as we can. So we have these shared backends, and then we just wrap all the input coming from CGI, XMLRPC, and WSGI. When we get the input from the user, we pass it and make sure it's safe. We put it in a dictionary. We love dictionaries. That's a very neat feature in Python. So grab it all in a dictionary, send it to the backend, which can then do the handling, interact with files, interact with the daemon running there. We also like the pickle module very much because you can just take these dictionaries, send them to file, and easy load later on. And the backend returns a list of dictionaries, so you can simply take that list. Either if you're using XMLRPC, you just receive that list with dictionaries in raw form, and you can manipulate it if you want. And in the case we want to display some HTML for the web pages, we have some output handlers that take the list and translates it to a string of HTML. So in that case, we need lists because we have to keep the order of the
individual dictionaries. As I mentioned, in relation to regrids, we have these external components. We use MiG for the wiki part. We use material for source code management systems. And of course, in these cases, we've used the CGI version as a simple CGI examples of these particular components. So you can actually install individual repositories and wikis into each of these regrid directories. So you just keep it all there, and you have all the files as part of the regrid directory structure. Then I found this forest board forum, which is probably not that well known. It's just a simple proof of concept that you can actually make a web forum in Python, and again it uses CGI. I extended that a lot to actually work with regrids. It's again pretty easy to read. And we have different other Python modules that just use that direction. And finally we have this zero install, the Python software that we use. This is not actually that much integrated with me because it's users and resources. Okay, so this is sort of a bit about how we actually do this FTP and SFTP MiG, where you can access your home directory in MiG through SFTP or SSH methods. So I found this wonderful SSH module called Parameter, which actually implements SSH in Python. So you get all the features of SSH and SFTP from this single Python module. And it already provided us with an example server for SFTP. So what we had to do to integrate it with MiG was we needed some way to use the grid authentication on authorization and some way to map to our MiG user homes internally. What we did was that we decided to have users provide their own SSH public key in their MiG code. So they go to MiG and they have an interface for specifying the public key. We use that key to let them access the user home. So we need to make sure that the users can only access their own home, of course. They should not be allowed to access other users' MiG homes. And they need to be able to access these regrids shared directories as well. So there's a filtering going on in the server. It's not that difficult to do. It's just you need to do it right. It's to make sure nobody can access what they shouldn't be able to access. Then we have another thing. We use symlinks a lot for making regrid shared directories appear as part of the normal user home. So in the user home, you just see these shared directories as ordinary directories because they are symlinked into the user home. So of course, we want to avoid users tampering too much with symlinks in their user home because then they could create symlinks to regrids that they are not actually allowed to access. Again, we just to avoid people shooting themselves in the foot, we also prevent users from changing permissions of the files. So they remove the right and the read and write ability of the files. But this means that we actually have a server that provides SFTP for the codes and users can use it as SFTP. I'm not sure I have time to go too much into detail about this, but generally this outlines the way we avoid installing software and resources. So the big idea is that we generate scripts on the MiG servers, push them out to the resources using SCP, then we execute those scripts using SSH, and those scripts will then do all the job handling, and we can stop and get later with SSH. So we don't actually install anything on the resources, we just push the stuff we need there, run it there, and clean it up afterwards. Okay, so since this is a Python conference, I should probably go into a bit of detail about our experiences with Python, what it gave us. I gotta say, it's been an amazing development. We've been able to develop this middleware to a point where we believe we can actually do a lot more than most of the other grid middlewares. We've done so with very little developer effort compared to the other big EU-sponsored projects. It's very easy to develop with Python because you can do very quick concepts, and it's not a far way to go from these concepts to actually have some production code. This time we have about 50,000 lines of code in MiG, and when we compare that to the millions of lines of code in other middlewares, you get the point. This also makes it a lot easier to maintain and get into further development because less code means less time to get acquainted with it. We are especially happy that we have this very easy and flexible data structure like dictionaries and we actually end up using dictionaries and people instead of databases. Could of course use lightweight databases, but in the end, in most cases, we are completely satisfied with just having dictionaries for most of our data. And the last thing I want to mention is this entire thing that I mentioned about having a backend module that is shared between different interfaces was very easy to make and still have these flexible output formats because string formatting and string concatenation is rather easy to use in Python. There are some template engines as well we could use with on that here. Okay, so at this point we tried to focus on having everything in Python according to our MiG rule. So at this point we don't have everything in Python. We still have an Apache web server running the core MiG. We could, of course, replace that with any of the Python web servers, for example, the native HTTP server extended with SSL support. We could use Django, we could use Zope, or any of the other models. The main concern in relation to that is we need to support user certificates, and we need some stability and performance that may not be available in these other frameworks. We haven't experimented much with it, but could be done. Then we still use SSH for actually sending these scripts to resources, stuff like that. We could extend that to use Parameter as well. That's simply a matter of time and effort that I think I will try. On the client side, if you want to go for the advanced interfaces and actually use the user scripts, then we still rely on curl to communicate with MiG because it supports client certificates. We can't really find a good solution for actually using user certificates in SSL connections to MiG. Well, you can use the Python socket module, then use SSL, but you still need to provide passphrase every time you open a new connection. And that's a bit difficult to integrate in dynamic applications. So far we haven't found a good way to do that in the future. And we have some other interesting things like we could use HTML template engines and stuff like that to generate all the output from templates instead of what we do now is just manually append strings. There are a number of things we can do here, but we've shown that it's possible to go even further using Python, but it's a matter of time, actually. So I'll try to sum up where we are now with MiG. From our point of view, we have a feature-complete grid middleware. You can do all the things that you want to do in a grid. Of course, you can always come up with new ideas, but all the things that we had in the original vision. It's rather easy to use. It's all web-enabled, transparent to the user. It's easy to use for the resource owners, so there's no incentive to say, oh, I don't want my resource built because it's too much hassle. We provide flexible resource sharing with different resource models, the dedicated resource model, public resource computing, and the latest edition of this virtual machines style. And then we have libraries for all this dynamic collaboration. And we saw a way to make simple applications using libre's web pages. We focused somewhat on dynamic software deployment with zero install. So that should be pretty easy by now to actually get your software on grid. So what's left for us is that so far it's been pretty much a research project. We haven't had these big production sites keeping us busy with the production-ready code. We do have a production setup where we use our grid for different research projects and for courses at the university, but it's not a big scale yet. And of course, that means we also haven't done that much in relation to actually get good performance when we want to distribute MiG servers and distribute that. Those are issues that we want to address. That's what I had. Just want to show this is the info page if you want to know something more about Fusion Grid, and then I think if there's any questions.
Yes, about the 10 minutes.
Myler Half spends a long time dealing with grid computing for CERN, doing a lot of this sort of stuff. And a lot of the time it's actually sort of doing bookkeeping.
Yes.
This looks quite nice. But how much outreach do you do with sort of junior level users of the grid for managing physics to see what features they really need and what problems they actually face?
Yes. Well, as you might have seen from the first slide here, my official association is now that I'm at the Physics Institute of Copenhagen University of Copenhagen. I used to be at computer science. But now we moved a bit closer to the physicists, and we do run projects to try to get more users acquainted with these easy interfaces and getting to know about the actual availability of things that shouldn't be so demanding for users to get started. We do try to get more users, and this is of course one of the opportunities.
If you want something.
Yeah, sure.
I have also a question, because I'm coming from the commercial high-performance computing. Have you any measures for license handling? So, for instance, if you have a lot of simulation codes or things like that requires a commercial license, it's availability of a license server. It's, in my experience, this is usually a problem that it's not easy to tackle this.
Yeah. Actually, I think I have some. We do try to cover that a bit as well. One of the things that we saw in practice was that in relation to MATLAB, we typically have this case where you have people choose to have a compiled host that they share because that is somehow feasible in relation to license. And in this particular case, the actual application platform that I showed here is MATLAB helper application. So all the users of this MiGrid can go to this application portal, submit the MATLAB code. It will automatically be sent to the compilation host with the license. Then they get the compiled version back to the MiG home, and then they can send it off to resources where they don't need the full license. I think they need some runtime license or something like that. But at least they need the runtime software there. But you get around the license issue by doing this. in a legal way.
Yeah.
Well, like, which license is this project under?
Minimum intrusion grid is GPL2, and we use some components that are either BSD or more free for some of the sub components. Generally, if it's at least it's GPL2 or free or more free.
So when a user submits a job, it has also to specify the resources that it is going to use. And what happens if the estimate is not good? For example, it says it's too low, it takes a longer time, or if it's too big, it occupies the resources too much?
First of all, if you specify less resources than what you need for the job, then you will typically end up having the local resource kill your job when it has used all the resources that you specify. It depends on the actual resource. The usual thing is that there's a local batch system running on the resource that will take care of that. That's one case. If you, on the other hand, specify too many resources, then it's not really a big deal. The only thing that it will result in is that the scheduler on MiG will have a harder time finding a good job slot for you, and you may end up having the job wait longer because you'll have to wait for a suitable job slot. This could be perhaps found early if you have specified something more close to what you need. Is that all the questions? Yeah.
You mentioned that one of the reasons people were moving from grid computing to the cloud was that you could put on your own image. And you talked a lot about how you do resource management, or dependency management, software dependency management, things like that. From using it, I know the reason that you built this is because no one likes having their job fail because they've missed out something in their environmental variables, things like that. Maybe this is naive, but would it not be possible to, instead of uploading a virtual machine, to be able to specify these things to the grid, then download something that would allow you to verify that your job would in fact work?
That's actually a good point. Part of the virtual machine project that we did here actually focused on specifying what you wanted in your virtual machine. That is the list of software packages. Then you could download the virtual machine image generated on MiG. You could even start your application, freeze it there, send it to MiG, let it proceed running on some big resource, and then pull back the result when you wanted to. These students who work in this did some really neat things actually with that. So I really look forward to getting that integrated in the production version of MiG. Because I started working on it earlier this month, but unfortunately the guy I collaborated with is out with illness for a while now, but I hope to get it done this summer sometime.
Is time only for one question more? You want to ask us a question?
And what about security on the data that are on the resources on the cloud and so on? So what happens if they disappear or something like this?
I mean, if you're thinking about user security, so I mean about user losing their data.
Your data and what if I use them?
Okay.
Or results in contact with results.
Okay. Yeah. So we have a replication of files in MiG, and we have backup of the user homes. But when you send files to resources, then the MiG takes care of cleaning up afterwards, removing any files you had there. Of course, you could have resource owners, if they have privileges, they can of course monitor all files on the resource. So you need to do some manual encryption or something like that to make it completely trusted.
Sorry, but the time is over, so we have still 5 minutes before the start for this talk.